Okay, so this says in the malonic and acetoacetic ester syntheses, we must use a base that matches the ester groups. So let's take a minute. We have our malonic ester, we have a base, we have our alkyl halide. What are these things going to form? So go ahead and pause the video, predict the product, and then come back. Okay, great. Nice job. So a lot of you probably said, oh, well, this is a base. It's going to form our enolate. That's true. And then we're going to, that enolate would add to that alkyl halide. That is also true. So the product of this is going to be having these three carbons attached to this position. And what else is going to be going on here? So this is probably the product that someone would desire at this step. We make our enolate, we add our alkyl halide. But what's kind of competing potentially in this reaction? Well, this is a base, but it's also a nucleophile. And one thing that we have is carbonyls, right? And this OCH3 nucleophile, we want it to just deprotonate here, but depending on just what it bumps into, it also has the opportunity to add to the carbonyls. So what's that going to do? Well, if we add to the carbonyl, that would make an intermediate that looks like this. And that looks like our tetrahedral intermediate type from chapter, from the last chapter when we were talking about all the carboxylic acid derivatives. And essentially, when we have our tetrahedral intermediate, the electrons collapse back down to reform that pi bond, and then whatever group is the best leaving group is the one that's going to leave. In this case, we have O- as a leaving group, or O-. So at this point, we could very much go back here, but also the ethyl ester could also be what acts as the leaving group. And in that case, we now have a mixed ester, which is not ideal. So we have this product, if the ethyl ester oxygen is the one that acts as the leaving group, and we have a methyl ester on one side and an ethyl ester on the other side. Why is this problematic? Well, when we run a reaction, we usually, take the reaction, we purify the product, and we want to characterize that product to make sure it's pure. But we are very likely to have this as one of the products, but also what we're going to see in our mixture is probably some of this mixed ester product as well, where we have ethyl ester on one side, methyl ester on the other side. We could also have a product where, and I'm just going to shorthand this one, where both of the esters were changed out to the methyl ester, and we have the alkyl group put onto that. So instead of having one product that is easy to characterize, we're probably going to have a mixture of three products that just complicates the purification and characterization of our synthetic products. So what does it say? We must use a base that matches the ester group. So this base, sodium methoxide, it's just a methyl group, doesn't match the ethyl esters. So how do we solve this problem? We just instead use the ethoxide base instead. If we use this ethoxide base, this is going to be the only product, and these two will not be there. But that's an important consideration when you're running these reactions, because you don't want to complicate purification and characterization for yourself if you don't have to. Yeah, all right.